You can
Yeah.
take that one.
Hi everyone, welcome to my tutorial. So as you can see, it's gonna be about limitations of state-of-the-art and a new principle framework for HPO, which I'm very excited to talk about. I'm Dravi. I'm really pleased to present at AutoML, this wonderful conference that I'm excited to be part of. I'll begin by thanking all the organizers, especially the tutorial organizers, who did a great job at putting together this workshop. Right, okay. So let's get started. So I'll start with just reminding everyone what a hyperparameter is. Like, it's not needed at this conference, but just sort of principle perspective, we can one sort of lens of viewing it as you can think of it as a special case of algorithm selection in machine learning, because you can think of each real or discrete value of hyperparameter corresponds to a unique algorithm, and you want to select by selecting hyperparameters or tuning hyperparameters, you're also tuning algorithms. So you normally think of algorithm selection as maybe deciding between decision trees or neural networks or what algorithm to use, but you can even view technically hyperparameter selection as a kind of algorithm selection. And why is it so common in machine learning, especially because firstly, we have hard problems, which means there's no single good algorithm. You need to try out different algorithms and in order to solve these hard problems. Right? And then there's data everywhere. So machine learning algorithms, by definition, work on data, and your algorithm must adapt to domain-specific data. So you need to tune the algorithm by setting hyperparameters to get the best performance. And by performance, I mean, everything ranging from model accuracy, training time, model size, stability, and hyperparameters impact everything. So you need to optimize all these several different objectives by carefully setting hyperparameters. All right. Now, in the context of industry, I'm an academic, but I have some slight view into industry as well because I had some experience at Google before starting my PhD. From my personal experience, I know that data preparation and hyperparameter tuning take up most of the ML research hours. So it is pretty time consuming, and that justifies this conference. We want to automate it. We want to automate this, right? So that's the whole point we're here. It takes up a huge amount of compute. That's another aspect. So you want to do it efficiently, and it's very critical in high stakes applications. And this is even more important when you think about LLMs today, where everything is magnified multiple because there are like billions of parameters and very large scale data and very large scale compute requirements. So it's becoming increasingly important to tune these hyperparameters in a careful way. Okay, with that motivation, I'll give you a roadmap for the tutorial. The first part will be about current approaches in practice. So as promised, we want to discuss what they are and then introduce what limitations they have, which we would like to address. So there are cool research questions and directions and what's missing, right? Then we look at machine learning for algorithm design. So since I said like hyperparameter tuning is a special case of algorithm selection, so you can view, we'll use machine learning for algorithm design. I'll introduce some fundamental concepts from learning theory, which have been used in this new principle framework. Then I'll give some applications to decision trees, neural networks, and I'll conclude with a quick review of future research directions. All right, so let's start with existing approaches. So historically, people have used things like grid search or random search for hyperparameter tuning. That's the first thing that comes to mind. You take a grid of hyperparameters, do some cross-validation. This can be inefficient. It's unprincipled. There are no sort of guarantees on like whether if you select points from the grid, there is no guarantee because typical performance variations as a function of hyperparameters are super non-convex. So there is no guarantee you'll get an optimal hyperparameter by selecting just the one hyperparameter from a grid. So you want something smarter. There is no transfer across tasks by using these data independent. And then recently there have been theoretical proofs, like if you use a grid for these specific tasks, including clustering and integer programming, then you will end up getting highly suboptimal values of hyperparameters. You can construct distributions and examples where this is the case. On the other hand, like more state of the art, so this is like a historical preview, but today people use a lot of this Bayesian optimization based approaches. gradient-based approaches, bandit-based approaches. So these are more of the things that people currently use in practice, right? And I'll introduce at least the Bayesian optimization and bandit-based approaches in this tutorial. So let's start with the focus here will be on theoretical understanding, as well as, how did they apply to continuous hyperparameters and like other limitations. So I'll go into the detail as we go along. Right. So let me first raise an interesting question, which is not answered by this current approaches, which is how does model hyperparameter actually depend, model performance depend on hyperparameter, right? So the short answer is we don't understand it. It's very complicated. It's a super non-convex function. And if you think of Bayesian optimization, it uses some sort of crude approximation. So it says, let's estimate this performance let's model it as a noisy evaluation of a complicated function with certain smoothness properties, which we do not know whether they're satisfied in a given concrete example of a hyperparameter. So we don't know what the right smoothness priors are, what the noise is, and how to search, like acquisition functions, which decide each sequence of next point. So there's a lot of actual hyperparameters in Bayesian optimization, which we don't know how to set, right? So that's one of the challenges. Right. So the core question which I want you to take away from this is this sort of more principled approach would try to capture what is the actual dependence of the algorithm's performance as you vary the hyperparameter. So this is something, of course, that depends on the algorithm and the hyperparameter in question. So if you're talking about learning rate in neural networks, that will have a certain functional form, and what properties of this functional form you can give, and so on. So this is, in other words, we are trying to like open up this black box optimization into a more white box approach, where we try to actually capture this complex but still tractable dependence. Right, so let me introduce Bayesian optimization for a quick background. It all depends on Gaussian process, which is a generalization of multivariate Gaussian distribution to functions, right? So there's a distribution over functions, and you can use it to model noisy evaluation of some function, right? So the mean is given by some function m of x, and there's a covariance between pairs of points. So each finite set of points are jointly Gaussian, right? So you can write down its expectation, you can write down its covariance using this kernel, and since all finite collections are assumed to be jointly Gaussian, you can compute the Gaussian, you can compute the conditional distribution. So given a finite number of observations, you have you can compute exact expressions for the distribution on the, given an observed points, observed number of hyperparameter computations, you can compute the mean and variance for the entire domain of the function. Right, so it looks something like this. So let's say you evaluate the hyperparameters for these 5 values. So you have these 5 actual points, and using your prior on the kernel and so on, you can estimate the mean and uncertainty at all the other points. That's what it looks like. Here's a nice picture. So you keep on querying points. So one of the things here is this green line called the acquisition function. So this is basically crucial in deciding which is the next point that you query. So acquisition function, there's a whole variety of them. It's like a whole design question in Bayesian optimization. But roughly speaking, you want to compute points with good mean, but also you want to initially, at least you want to figure out points which have high variance, like more uncertainty. So you learn more about the function by querying points and high variance. So you want to do some combination of mean and variance, and that's basically what this acquisition function tells you. So sequentially you pick up points which maximize the acquisition function, and there's some true function, but you by doing these evaluations, you get closer and closer estimates of that true function. As I mentioned before, Bayesian optimization has its own hyperparameters. One example of a crucial hyperparameter is this parameter which, roughly speaking, estimates the smoothness of the function. So basically what this is saying is, how many, let's say, oscillations are there in the function. And it's something that you have to tune manually to figure it out. But if you have an understanding of the actual structure of which we'll go in detail in the rest of the tutorial, if you have some understanding of how many oscillations or how smooth the actual function is in a particular hyperparameter, you'll be able to set these hyperparameters more automatically, right? So you wouldn't need that manual effort of trying to figure this out. There is some work which by the group from Andreas Krause, which develops a technique which considers like a growing set of functions. So it considers a small set of function. If the smoothness conditions are violated, it considers a larger set of. It's a fairly slow approach, not a practical approach, but at least it has some guarantees. So there's some examples of approaches which handle this, but it's an exciting research question of how to automate this process of getting the structure correct and the smoothness priors correct instead of having to do this manually. Right. There's some other great tutorials on Bayesian optimization. I would love to go in more and more details, but I think at this point that's not the main focus of this tutorial. So I will refer to some other great tutorials by other people, and I would recommend you to check them out. Right. The other approach I want to talk about is bandit-based approaches. So these are bandit problems which have hyperparameter specific assumptions. One example of that assumption is as you keep on doing several iterations of your training epochs, you will the hyperparameter's performance converges to something, some certain limiting value for each value of the hyperparameter. So you can model that as a non-stationary bandit. So each time you take a value of a hyperparameter, for example, a learning rate in your neural network, and you sort of set that hyperparameter for a particular epoch, run it, you get some accuracy gain. But you want to, instead of getting full learning curves for all values of the hyperparameter, which is super inefficient, especially when you have multiple hyperparameters in high dimensional spaces. That's very hard to do. What you do instead is you do a few number of iterations for each hyperparameter. You sort of reject some hyperparameters early. So that's how you model this as a bandit problem, right? And eventually you want to figure out which are the more effective hyperparameter values by some sort of approach like successive halving. You sort of throw out half the hyperparameters after a certain number of iterations and so on. Another interesting bandit model, which is more recent and more upcoming, is this thing called rising or improving bandits. Here, you also take into account the structure of this trajectory. So here we have, you can model the learning curves. It's a simple model. Maybe the average learning curve is like a concave function, right? There's some diminishing returns aspect to it. So not just talks about the limiting value, but also how the trajectory goes. And if you assume the rewards are going to be concave, then it's a concrete mathematical problem. You can give sort of nice algorithms and guarantees for those algorithms. So this is another nice principled approach towards modeling hyperparameter tuning as a bandit problem. So there are some known guarantees, I would say, which are already pretty exciting. So for example, for Bayesian optimization, there are regret guarantees, but these regret guarantees kind of depend upon your algorithm, your Bayesian kernel being set properly, or your acquisition functions having some right parameters, like the noise parameter matches the noise, which is not known to the algorithm usually. So there are guarantees for GPU CPU, but this sort of assume that your algorithm has some knowledge of these unknown parameters. There are guarantees for bandit-based methods. One of the limitations, and they're very nice, but their limitation is they only apply to a finite set of arms. So they don't apply usually to continuous parameters, which is very common in AutoML. So these are some individual limitations, but the overall limitation that I really want to highlight is that both these approaches are black box. They don't really take into account, there are some structural aspects in bandit problems, but they're also super general. They don't take into account the actual behavior as you talk about a specific hyperparameter, and they're not able to take that into account. So that's going to be the focus. This leads us naturally into how do we open up this black box and see can we develop techniques which take a hyperparameter and an algorithm and, figure out how the performance varies as a function of the hyperparameter. Okay, so before I get into that, I will take a quick detour because I want to introduce some useful tools and terminology, which will help us understand how to approach this. So I'll introduce some learning theoretic foundations and concepts which are introduced in learning theory, but I think are super helpful in understanding hyperparameter tuning. Right. So this framework goes under the name of data-driven algorithm design. So again, so this is we generalize hyperparameters as algorithm family. So this could be used for both hyperparameter optimization as well as algorithm selection. As you have a family of algorithms, they could be either tunable hyperparameters, or you could take two heuristics, you can interpolate them and generate a whole family of algorithms. Like, in linear regression, there's L1 penalty, L2 penalty. You can interpolate between the two to get combined L1, L2 penalty, right? So these are good examples of hyperparameters, but this everywhere in AutoML. The framework takes into account these repeated problems. So you not only solve a fixed instance, but you have clustering, or if you're an email server, you see new emails every day. So you're kind of solving the same problem in a repeated fashion. And you want to figure out maybe these problems are coming from some distribution, or which is like this optimistic setting, but it might be also an adversarial or changing sequence of problems. So there's a whole range of settings under which you can formulate these sequence of problems. But the idea is, from your past experience of problems that you've solved, you should be able to figure out how to set the hyperparameter in the current problems. So you should be able to leverage your experience and previous problems to design the model for the current problem. Here are some technical challenges. I just give a highlight of this. Algorithms are an interesting concept space. So you think of things like neural networks or decision trees. They themselves are algorithms, but then if you think of hyperparameters, they form a different concept space. They consider they have interesting properties like sharp transition boundaries. So they're not nice convex functions, but they're not necessarily not only non-convex, but they might not even be continuous in some sort of discrete optimization cases, which we'll talk about. And it's also more challenging to handle multiple hyperparameters. So these are things that we'll see as we go along. And just a little bit of math, just to ground everything. We talk about a problem instance. So it's super general. So you have a problem instance from some set X, and you have an algorithm family A. So A is a collection of algorithms, maybe defined by your hyperparameters, and you have a distribution over X. So your problems could be like clustering instances or semi-supervised learning instances, or whatever you want to solve. They're coming from some specific domain. So the domain specificity is captured by the distribution, and you have an algorithm like email spam filtering or recommendation algorithm. So those are your algorithms. So you want to tune those algorithms to fit the application that you work on. So this is sort of the basic notation that we all stick with. All right. Some quick examples. So in this emails on email server, you get a bunch of new points every day, new emails. And in the semi-supervised learning setting, for example, somebody marks some emails as important or spam manually, but for the vast majority of emails, you don't get any information, so they're unlabeled. So you get this sort of semi-supervised setting. You get some labels and some unlabeled points, and you want to figure out how to classify all points, right? That's this. You can both do like statistical learning as well as online learning. So online learning is when you don't assume anything about the sequence. There can be an adversarial sequence of problems, and you still want to give some learning guarantees. I won't go into too much detail here, but just one example where we could tune hyperparameters using these techniques. Another example is decision trees. This one I will go into some detail in this talk, but there are different aspects of decision tree learning. You can build a decision tree top down by selecting successively which node to split and what feature to use or which rule to trigger at each node. So building decision trees, Bayesian methods, there are different hyperparameters in this, and I'll give some examples of this later in this talk, but this is another example where we can formally analyze how the algorithm's behavior changes with these hyperparameters and give guarantees on how complex that behavior is, how to tune that, and so on. So there are some other related lines of work, algorithm configuration, which also has a nice tutorial by Kevin Leighton Brown and Frank Hutter. That indicates that these approaches have practical success. The connection with our line of work is we give theoretical guarantees. So there's already good practical evidence of these things working, but we complement that literature by giving theoretical guarantees for those approaches. There is connections with meta learning or learning to learn, because they're also you have different tasks. So you can think of different problem instances and different tasks as different tasks, and you're trying to learn a common way to solve multiple tasks. So there are formal connections between meta learning. Meta learning one formal connection is that it sort of lies between the two extremes of distributional setting and online learning. It's an intermediate, more realistic setting between the two optimistic and pessimistic extremes. And finally, we have learning augmented algorithms, which also uses machine learning for algorithm design, but in a different way. So they assume you have some predictions using a machine learning algorithm, and then you can design better algorithms using those predictions. But this doesn't quite give you how to come up with those predictions. And somehow this data-driven algorithm design literature tells you how to use machine learning to actually use data to give better algorithms. Okay, so with that, I'll move on to some learning theory concepts. The first concept is this notion of primal and dual functions. So remember, we had this input space X, and we have the space A of hyperparameters or algorithms. You have any performance that could be like memory or accuracy or running time. So you have a function which, if you apply algorithm A from your family on input X, you'll get some performance. So this is the function which captures this entire performance. Let's say it's a bounded function. So the primal function is when you fix a hyperparameter, it's a function of, as you vary the it's a function of the problem instances, this is the function whose complexity we care about in order to give guarantees on tuning hyperparameters. There is a dual function where you fix the problem instance, you vary the hyperparameters, and then you look at that function. And so these are both like marginals of this joint function, but an interesting part of the theory which we'll get into is somehow the structure of the dual functions is nicer, and it allows you to give guarantees more easily. Right, so that's one concept that we'll need. Another concept from learning theory which we need is this analog of VC dimension called pseudo dimension. So the standard question in learning theory is you have some approximation epsilon, you have some confidence delta, and you want to give how much data you need to be epsilon close to the best algorithm or the best hyperparameter with high probability 1 minus delta. So this is a sort of question of sample complexity, and one of the standard measures is pseudo dimension, which roughly measures how complex, the complexity of the function class in terms of how many instances it can shatter. So roughly speaking, if your function class is very complex, it would be harder to learn. You'll need more data to learn it. And by shattering, we just mean if you have sign patterns. So by sign pattern, you have like n instances, and you want to get above below sign patterns on those n instances. By above below sign patterns, I mean you have some thresholds, and the performance is above as well as below a certain threshold on each instance. And you're able to if your function class is super complex, you will be able to generate all 2 to the n different sign patterns. So that means like you have a super powerful function class, and that's harder to learn. So this is a sort of a natural measure of complexity. If you've seen learning theory before, you might have seen, you probably have seen VC dimension, which does the same concept but for binary functions. This is a natural extension to real valued functions. And by classical learning theory, if the pseudo dimension is finite, then you have a direct implication on sample complexity. So you have this result which says in terms of your epsilon and delta in the pseudo dimension, you have a bound on how much data you need to get this probably approximately correct value of optimization of this function, right? So the interesting question in hyperparameters is actually bounding this pseudo dimension, which is non-trivial. Because, yeah, question?
Yeah. Like given this kind of bounding thing, right? Does this somehow depend on how you, or does this account for like the distribution of points or something? I mean, if you optimize, right, you kind of sequentially select your configuration. Does this account for that? Because if you like sample from just a specific region, right, and it kind of gets stuck there, at other regions you won't get enough information to like model.
That's a great question. So so notice here that the bound doesn't depend at all on the distribution here, and the reason is the pseudo dimension bounds apply for arbitrary distributions. So it applies for worst case distributions, like if the distribution only samples some very hard problems or very easy problems, it applies in both cases.
Yeah.
So this is a more worst case bound. You can hope to give better bounds. That's a very great question. I'll point, this comes up in actually the very end when we talk about open questions, but we do have one first work which tries to, for example, if you have a nicer distribution, like a Gaussian, your data is coming from some simple distribution, like a Gaussian distribution or sub-Gaussian distribution, then you can get sharper bounds than what you get from this approach. So as you can imagine, like if you want to work with worst case distributions, you would need more data, but if you make more assumptions on your distribution, you can get sharper bounds.
Yeah.
That's a great question. Right. So for the majority of this talk, we'll work with this pseudo dimension notion, which actually works for arbitrary distributions. So these are more worst case bounds, but they apply to everything. So you can be more rest assured. You don't need to. If you have this much data, then I'm happy for worst case or adversarial or like extreme cases for distributions. Great. So let's think of a simple example for where you can bound a pseudo dimension. So suppose you have straight lines in 2 dimensions. You have this function class which has 3 parameters. It takes a point xy and then it maps xy to ax plus by plus c for some real values a, b, and c. So what's the pseudo dimension? If you've seen VC theory, the answer is 3. Again, I'm just giving it away. So the idea is you can shatter. So the idea is to come up with the largest number of points that you can shatter. So you can label in all possible ways. So with 3 points, you can do that. But if there are 4 points, there is a configuration where by using straight lines, you cannot generate all 2 to the 4 labels. But for 3 points, by using straight lines, you can generate all 8 labels. So this is an example of how being able to generate sign patterns corresponds to the strength of the function family. This is a very simple, like linear boundary. We work with more complex functions like neural networks and more complex like nonlinear boundaries. But this illustrates the idea of how pseudo dimension is helpful. If you go in D dimensions, there's a natural extension. So in D dimensions, it's D plus 1. Here, the answer is 3 in 2 dimensions. So these are simple examples of calculations you can do to capture the complexity of your function class. Okay. Coming back to primal and dual utility functions, so there is this brilliant seminal work which gives like a general result in terms of the VC dimension and pseudo dimension of the dual function. That's the reason why I talked about dual functions. So in order to, so the sample complexity depends on the pseudo dimension of the primal function, but that can be hard to analyze. Remember, it's a function of two variables, the problem instance and the algorithm. But if you look at the dual function, so you fix the problem instance and as you vary the algorithm or the hyperparameter, you're typically able to give nice structures. The structures are often piecewise, so you can give guarantees like piecewise linear with, there are linear boundaries with, and within the boundaries, maybe the function is, the behavior is polynomial or something. So this is just an example, but you can have, in terms of the complexity of the boundaries and the functions within those boundaries, you have this sort of general result for pseudo dimension of the primal function class that we care about. So the nice result which captures, which can be applied generally. One of the issues with this is you still need to be able to give bounds on the VC dimension of the boundary functions and the piece functions. So that's something we tackle using some different approaches. Right, so give an example here. In clustering, if you've seen linkage clustering, it's a very natural approach to clustering. So you have a collection of n objects and you want to organize them into a hierarchy. So you have, this is an example which I used in an earlier tutorial I gave. I should have updated this to AutoML, but I think I use the same slides. So you have n objects, you organize them into a hierarchy, for example, you're categorizing news. So you do this sort of natural merging process. Anything that's similar will be merged into a group and then a higher level group and so on. So that's a natural approach to clustering. You start with each object as its own cluster and you repeatedly merge the most similar clusters. So, and then at the end, everything becomes like a single cluster. So this is one way to hierarchically cluster objects. And in this case, there are several heuristics which define what is most similar. So the key definition or the key heuristic here is how do you decide two clusters are similar? So one approach is single linkage, which says two clusters are similar if their nearest points, like if you consider the points which are closest between those two clusters, they have the closest distance. So that's one heuristic. Another heuristic, if you consider between pairs of clusters, what's the furthest point between those two clusters? And if that is smallest, you say that these are the most similar clusters. So that's complete linkage. And there are other bunch of heuristics you could use. Here you can directly apply the previous theory. You can show that so one thing you can do is you can show this, if you interpolate the two algorithms, so you have this hyperparameter which interpolates between the two heuristics. So you can generate automatically this family of clustering algorithms. For one value of the hyperparameter, you get single linkage. For another, you get complete linkage and you get everything in between. You can show that this has piecewise constant structure. So as you vary this hyperparameter, you get this one-dimensional piecewise constant function which captures all the different behaviors of the algorithm, all the different clusterings it can obtain. And even though the total number of clusterings you can imagine is exponential, but as you vary this hyperparameter, you only get a polynomial number of different pieces. So that's one thing you can show, and that implies a bound of the pseudo dimension. So this is one nice example where we can use this general result on for bounding pseudo dimension. Right. The question really is we want to be able to tune this hyperparameter alpha. Right. So we have also extensions of this result. So this is something we just showed in a recent thing we put on archive. You can do both algorithm and hyperparameter selection by bounding pseudo dimension. So you can, if you have k algorithms, A1, A2, AK, and for each algorithm, you have a family of hyperparameters. Like you have neural networks with a learning rate, decision trees with some other hyperparameter, maybe a third algorithm with something else. So you can, this is sort of a general tool which gives you a bound on the pseudo dimension when you're trying to select between the hyperparameters of different algorithms. And the dominant term, as it turns out, is the complexity of the most complex hyperparameter class. So that depends on max I of the pseudodimension of each hyperparameters. So in some sense, it reduces the, right, there's a logarithmic dependence on the number of algorithm families, but the dominant term is this. So in some sense, it reduces the problem of hyperparameter, combined hyperparameter and algorithm selection to just hyperparameter in the worst family that you're interested in. Right, so this is a nice, interesting theoretical result. Yeah, with that, I will introduce a second tool. So the nice thing about this framework that we've talked about so far is super general. It applies to literally everything, but then we don't have concrete ways to bound pseudodimensions or VC dimensions. So like if I give you something like neural network and this learning rate, can you bound the VC dimension and pseudodimension? Well, if you were able to do it, you can apply this theory, but how do you actually do it, right? So here's a nice framework which potentially allows you to do it. It's called the GJ framework. So it's almost 30 years back, there was this nice tool for giving bounds on pseudodimensions, which was recently revisited in the context of data-driven algorithm design. So the idea is if you have an algorithm which performs certain kinds of operations, you give, it can do things like addition, it takes in some hyperparameters, it can do some things like addition, multiplication, subtraction, division, and so on. You can give the pseudodimension bounds in terms of the running time of the algorithm. So that's a nice result from the 90s. And we provide more refined versions of these frameworks, so including some other groups and our group, we have more refined GJ frameworks, which I will now describe. Right, so if you look at the GJ algorithm, you have n real hyperparameters. So it applies these either arithmetic operations on these hyperparameters, or it's allowed to do conditional operators. So it can do an if then else, right? And it outputs something like a cluster or a matrix or some whatever your algorithm is trying to output. And the key idea is, in this case, all expressions that the algorithm ever computes are going to be rational functions or ratios of polynomials of its inputs. Because if you're only allowed to do this additional multiplication, addition, subtraction, and division, you'll only get ratios of polynomials in the original hyperparameters at each node where you're trying to do these calculations. So another visual. So this is like a nice visual way to look at it, but you get this nice guarantee on pseudodimension bound, which depends on the degree of these rational polynomials, but also the number of distinct expressions that you ever compute, right? Visually you can see this as like you have this tree of computations, and each node you will compute some rational expression, and if it's greater than 0, you do something, less than 0, you do something else, and so on. So you can express the computation of your algorithm in terms of these calculations. And once you do that, the pseudodimension depends on the total number of expressions you ever evaluate and the degree of the expressions. And here is simply the total number of hyperparameters that you already know. So you can give a direct bound on the pseudodimension. It depends on, so even if you have like exponential number of expressions, the pseudodimension is fortunately only logarithmic in the number of distinct expressions. Right. So just a nice example of this is if you have linear regression, you have this ridge penalty. So you have regularization strength in linear regression. You want to minimize the validation loss. You want to tune your lambda hyperparameter to minimize validation loss in linear regression. When you apply this GJ framework, you know that the ridge solution has this nice closed form. So if you try to analyze this closed form, you can express it as a rational function where you can bound the degree of this function in terms of the number of features, and you can also bound the number of distinct predicates. Well, in this case, the number of predicates is just 1. So you get a bound on sample complexity by using this GJ framework very directly, right? So this is a much easier tool to compute pseudodimension. All you need to do is you look at the expressions the algorithm is calculating. In this case, it's a single expression because it's a closed form solution, and you bound the degree of those expressions. So that's all you need to do in order to get a bound on the pseudo-dimension. Another example is elastic net. So now you add another hyperparameter which does L1 penalty. In this case, you get more than one. Since this has a piecewise structure, you get more expressions. So that you can show that there are 3 to the d different number of pieces, and each piece has a closed form solution with bounded degree. So you can still use this technique to give bounds on the pseudo dimension here. There's another application I wouldn't go into much detail, but then, another thing you often want to do is low rank approximations. You have a matrix, it's useful to get low rank decomposition of the matrices, like a sparse matrix with the smaller rank, which still approximates the original matrix. And there are nice algorithms, and you can tune the parameters of this hyperparameters of these algorithms by directly applying GJFM. It simplifies this whole process of bounding pseudo dimension of these complex algorithms. Right. So rational functions are good, but you want to be able to go beyond rational functions, because often you involve computations, things like logarithms, exponentials, and the previous theory sort of just doesn't apply. So this is this nice idea of a general class of functions called Pfaffian functions. So if you take the derivative of the function and you can express it as a polynomial of the variables as well as the function itself. So when you take the derivative of exponential, you'll get e to the x, the derivative is e to the x, so it's a polynomial of the function itself. There is the notion of chain length. So the chain length is, you can chain several functions, and each function in the chain should have its derivative expressible in terms of all the previous functions in the chain. So that's a nice example of an example where you can still hope to give pseudo-dimension bounds in terms of the chain length, the degree, as well as the Pfaffian degree. The Pfaffian degree is simply the degree of the polynomial in the derivative expressions. Right. So here are some examples to make this concrete. This seems like a strange and foreign concept. It's really not. It's just all these familiar functions that you see, exponentials, logarithms, and even fractional exponents, they can all be written in terms of Pfaffian functions, right? So I'll give some quick examples just to show how you can bound the chain length and degree and Pfaffian degree of these functions. So, right. So remember, these are the definitions, and we are interested in this expression e to the 2a plus a cube. So, what's the chain length here? Right. So actually, one important interesting point is that there's no unique way to design a chain. So you need to design a sequence of functions, and you want to express their derivatives as polynomials of functions in the sequence. Right. So here, one way is you can just put the entire function as your function in the chain. So you just put the entire function there, you compute its derivative, and it turns out the derivative can be expressed in terms of a polynomial of the original function. You can subtract out the a cube, so you get something else, which is still a polynomial of the original function, and the you get some bound on the chain length, the Pfaffian degree, and the degree. Another more natural way perhaps is to just take the function e to the a in your Pfaffian chain. Its derivative is just itself, so it has Pfaffian degree 1, and then you express the function that you have as a polynomial of e to the a and the variables. In this case, the degree is larger with the Pfaffian. So there's multiple ways to express this, and each way to express it will give you a different bound. Similarly for log, this is a little bit more tricky because if you take the derivative of log, you will get something that's not polynomial, 1 over a. So how do you express it as a Pfaffian? The trick is you can add another function in the chain. So you can have 1 over a in the chain. The derivative of 1 over a is a polynomial in 1 over a. It's a degree 2 polynomial in 1 over a. So you get a Pfaffian degree 2, and you can basically construct a chain to also show that logarithm is also a Pfaffian function. Similarly, you can do it for fractional exponents. You get a slightly longer chain here. But again, you can use 1 over a as another initial function to give bounds on the Pfaffian chain length and Pfaffian degree. Okay. So with that introduction, why do we care about Pfaffian functions? Because we can give the sample complexity bounds for tuning the hyperparameters whenever there's this Pfaffian function computations in your algorithm. So your algorithm is still allowed to do those arithmetic operations if then else, but it's also allowed now to do Pfaffian computation. And you can give a boundless Fourier dimension in terms of the chain length of the Pfaffian function, the degree, the Pfaffian degree, and the total number of expressions that the algorithm computes. So this is a generalization of the previous result that for GJ algorithm that we knew for rational functions. Right, coming back to the clustering example, so suppose not only you have this single and complete linkage, but you also have multiple distance metrics, right? So you have different feature spaces, and each feature space defines its own metric, and you suppose you do a linear interpolation of these distance metrics, right? So this, if you do you get this sort of complicated expression for interpolating linkages as well as distances, but all these expressions, these exponents and these linear interpolations can be expressed using Pfaffian functions. So that's the sort of key takeaway, that you can use this Pfaffian, you can compute the total number of expressions this algorithm computes in terms of the hyperparameter. If you can bound the total number of times you do that, you can get you can tune these hyperparameters, right, alpha and beta, which interpolate multiple distance metrics as well as multiple linkage procedures, right? And you can directly get these sample complexity bounds for tuning alpha and beta. So I won't go into the details here, but the nice thing is that the Pfaffian GJ framework directly applies. Right, so I'll skip the details because in the interest of time, that you can compute these expressions, you can show that they have so many expressions, and that's the sort of whole idea of giving the chains. You can construct chains in terms of the logarithms and individual distance metrics, right? But just to summarize all the calculations, you can give a bound on the total number of chain lengths. So that's the number of functions in your chain, the degree, the Pfaffian degree, and put together that, you just plug it into our general result and you get a bound on the sample complexity. Right, okay. So those are, like, clustering is a nice example, but what we really care about is, can we apply these techniques to tune some real algorithms, right? So how about things like people actually use, like, decision trees for tabular data sets? People still use decision trees or decision forests for interpretable machine learning, as well as data sets which involve tabular data. Neural networks, of course, I don't need to motivate that, but it turns out you can tune hyperparameters here using these sort of general tools that we've been talking about. Okay, before I go into that, I just want to say that the applications are numerous. There's a growing research direction, and more algorithms and hyperparameters that you can tune, and not just in machine learning, but even beyond, to statistics, optimization, even just fundamental algorithms in CS theory, computational biology, mechanism design. So this is the whole field is less than a decade old, but we are finding a new lens with which to view algorithm design fundamentally, by being able to use machine learning to design your algorithms or tune hyperparameters instead of using heuristics or doing that manually. And overall, in this entire field, there are these several sort of major open questions and research directions. So you want to examine maybe other fundamental algorithms or hyperparameters. So this is just, we're sort of scratching the surface of which algorithms can be tuned using these techniques. There is, in this tutorial, we'll focus on sample complexity. So we've talked about pseudo dimension and how it impacts the amount of data you need to tune these hyperparameters. But computational efficiency of tuning these hyperparameters is an interesting question, and there's much less work on that. And the sample complexity, we talk about giving upper bounds on the sample complexity, how much data is sufficient, but there's also questions of like lower bounds, which are known in some simple cases like linear regression, but not in all cases. So that's another sort of active area for current research. Okay, with that, I'll start this discussion on decision trees, which is a concrete, cool application of these techniques. Just quickly check how I'm doing on time. Okay, great. So we want machine learning to be interpretable. So we have, we have these deep networks, which we are increasingly actually already using in things like healthcare and legal systems. But how do you trust the decisions of these machine learning models, right? So we want to make these complex decisions using, but it's at least deep networks are so black box. So what are the key factors? We want to, at least in these applications, we want to be able to justify when you make decisions about how do you make these predictions. So here come decision trees. So they are naturally sort of the gold standard for interpretable machine learning. So each internal node corresponds to an actual rule that gets used in making the decision, right? So for example, you're trying to decide whether you want to screen someone's lungs or not, and you want to be able to tell how you came up to that decision in healthcare. It's important to be able to justify to your patient like why we are doing this, giving you this medical advice. So you train this learning model, but if you use a neural network, you'll not be able to explain. But if you use decision tree, you can tell exactly, we looked at smoke, whether you smoke or not, your age, and these are all the factors that went into our decision of deciding whether, we give you this medical advice. Right, so decision trees are fantastic. They are so naturally interpretable. But even something as simple as decision trees, it turns out it's hard to learn optimal decision trees. There are several useful heuristics, but getting the best decision tree is also like an NP hard problem. Not only that, even approximately learning a decision tree is hard. So there's even more recent work in the last few years which show that getting an optimal decision, like within constant depth of an optimal decision tree, is hard, provably hard. There is a related line of work which talks about fast or optimal decision trees. So it's still exponential time, but like somewhat faster than what would be the naive algorithm. So there is exciting works both improving more hardness and more faster but exponential time algorithms. Here we'll look at a greedy approach. So this is guaranteed to be computationally efficient, but it's a heuristic. It does not guarantee to give you the best decision tree or the optimal decision tree. But let's look at it anyway. So you have this top-down decision tree learning, right? So you start with a single leaf node, and while there are at most t leaf nodes, you split each leaf node using some function f. So the function f could be one of the rules like age or smoking or some feature compared to some value, and which tells you whether you want to go left or right at that node, right? Right. So you have all these features, smoking and age comparison with different thresholds, and we apply these decisions at different nodes, and you split it to obtain further leaf nodes. So the key decision you need to make is which node to split next. You're building this tree top down. You start with a leaf node, but which node to split next and which rule to trigger at that node. So that's the key decision you need to make when you're building a decision tree, right? And that's where the splitting criterion comes in. So that's just what heuristic you use to decide which rule to use and which node to split next, right? If you go in Python today, like you'll see several libraries for decision trees, but they will always have like a list of splitting criterion, which as an applied researcher, you will need to manually select between these different criterions, right? And here at AutoML, we want to automate everything. We want to be, we don't want someone to go and manually try out all these three different or several different splitting criterions, but maybe is there an automated way of selecting the hyperparameter? So this is what we come up with. So we propose that we have this general expression which captures several different splitting criteria that people have studied in the literature, entropy, gene impurity, and even some other criteria that people have proposed in the theoretical literature. So there's this thing called alpha beta Chalice entropy, which has two hyperparameters, alpha and beta, but by setting different values of hyperparameter, you can select the splitting criterion, right, or select the algorithm by hyperparameter tuning. Right, so for certain values of alpha and beta, you will get gene impurity. For a different value, you get the Kearns-Mansour criteria, you get entropy. But there's also an infinite other values of these hyperparameters. So you get a whole family of algorithms for learning or tuning decision trees, right? As you vary alpha and beta on different data sets you observe, there are different values of hyperparameters that give you the best performing decision tree. So this just motivates that you need to find the best value of alpha and beta on your individual data set. Again, we can almost directly apply the tools that we've been developing in this context. You can give guarantees on like how much data you need to provably tune these in terms of the size of the function class, the depth of the tree, and so on. So you can give these many problems. This is the bound of the problem samples you need in order to tune alpha and beta. So you get sample complexity balance using everything we've been sort of talking about. There are some proof insights, but the key takeaway here is you want to just give upon a total number of distinct behaviors or predicates in the GJ terminology that the algorithm can take. So as you vary alpha and beta, what's the total number of different decision trees that you can possibly make? So that's roughly speaking what you want to give a bound on. Is if you can do that, then you can apply the tools that we talked about and get a bound on the pseudo dimension and sample complexity. Okay. There's another interesting thing you can do. You can not only optimize accuracy, but with decision trees, you also care about things like interpretability. And one measure of interpretability is the number of leaves in the decision tree, right? So here you can, this also has connections with complexity pruning. If you've seen that, but the idea is there's a hyperparameter eta which controls interpretability versus accuracy. So your accuracy is in this loss function and your interpretability corresponds to the number of leaves in the tree. You want to also keep that small to keep the decision tree more interpretable. So you can just modify this objective and art theory and techniques apply to even this modified loss objective. You must have, if you've worked in decision trees, you probably have seen gradient boosted decision trees. So this is using an ensemble of several decision trees. They have a collection of k trees, and you have a loss function that combines the weights of leaves in different trees, right? So you can use, again, this has a natural L2 penalty hyperparameter, an XGBoost if you've used that before. This is the state-of-the-art approach. So there's recent works showing that they beat even neural networks on tabular data sets. And we use a GJ framework-based analysis to tune this, to guarantees on tuning this lambda hyperparameter and XGBoost. Right. Again, the overall idea is similar. You give a bound on the total number of distinct predicates. And using that tools, the analysis is simplified significantly. It's much easier to come up with a proof for the pseudo dimension using our tools. Okay, for decision trees, there are several interesting open questions. So we had this recent UI paper, but we have current work, and I think also lots of exciting questions like how to more efficiently implement the algorithms for learning the decision trees. Lower bounds, we have upper bounds and sample efficiency, but in this case, we don't have lower bounds. Maybe online learning is another interesting direction. Can you give other guarantees like robustness and decision trees? Those are several interesting directions. With everything that's been building up, so I'm excited to finally talk about neural networks, which is something that everybody uses today, so this is overall, just to give some context, I worked on this framework for my entire PhD, like 5 years, and only towards the end and almost after graduation, I realized that, okay, now we have enough sophistication in these techniques to actually apply or say something about hyperparameters that you see in neural networks. So this is all ongoing work or under submission or future work. So super excited to actually show that these techniques can basically be used to analyze behaviors of hyperparameters in neural networks. So as you vary these hyperparameters in neural networks, you can characterize how the performance or the neural networks behavior will change as you vary these hyperparameters. Okay. So recall again, we have some real valued hyperparameter. Let's maybe simplify things a little bit. Let's focus on a single hyperparameter. There are some cases where we are able to handle multiple hyperparameters, but here let's focus on a single hyperparameter. You have also a notion of a parameter. So this is just the weights of the network. So you're learning a neural network. Each your network has some weight matrices which map your input to the output. The difference is your hyperparameters, they're fixed during training, but your parameters, you use backpropagation to update the parameters of your neural network. So just an example, if you have activation functions, right? So you have a neural network which have model weights, let's say W, and you want to use this parametric ReLU activation. So it's a ReLU, but there's like a parameter on the negative slope. So instead of being 0, it's like a slight negative slope. And by tuning this parameter A, you can potentially get better performance than just using vanilla ReLU activation function. So this is an example of a hyperparameter. In general, you can also interpolate any pairs of you can take two activation functions and interpolate them, and you can try to learn this hyperparameter. Right. So this is what we call as model or architectural hyperparameters. So these hyperparameters, they impact training. So once you set this activation function hyperparameter to a certain value, the network that you learn will depend on the hyperparameter that you selected. But this hyperparameter will also be a part of the final network that you learn. So it will still be used on test instances. There are some other examples in graph neural networks, but I want to contrast this with optimization hyperparameters, which are used in the training procedure, like learning rate, but they're no longer relevant once the training is done. So these hyperparameters usually impact things like efficiency of the training, but they do also impact, learning rate will also impact the accuracy of the network, because if you set it too poorly, you might not converge to a nice minima, for example. So just want to distinguish between these two hyperparameters, just because the techniques that we use for giving guarantees about these are very different. Okay, so let's start with the model hyperparameter. So there is this notion of a function which basically tries to capture everything. So you take a problem instance X, you have a hyperparameter alpha, you have a parameter or weights of the network W, right? And you can model the training of the neural network as taking this supremum function. So let's say you learn the best weights once you fix the hyperparameter. So for one value of the hyperparameter, you do your network training, you get this function. So this function essentially captures the performance of the network as a function of the hyperparameter, right? So on any fixed input X, it will tell you, as you vary the hyperparameter, this is how the network's behavior will be. So this sort of already captures the training process by doing this maximization over the weights. There are some examples. You can have, for example, you're using neural networks to regression. You can have this L2 squared loss, and your function f could capture the squared loss, for example. But it could be any function, really. Just recall this formalism in data-driven hyperparameter tuning. So you have this parameter alpha, and you want to figure out a parameter from your data which is close to the optimal parameters. The optimal parameter gives you the best performance on average over the distribution. you want some alpha hat, which gets using some training samples, which gives you almost optimal performance. Right. So how in the sample complexity question is how many problem instances or data sets, data points are enough to give this kind of guarantee, right? And this is what all this, just recalling everything from the statistical learning literature. So you have this pseudo dimension, and you can use the pseudo dimension concept. The idea is now you want to bound the pseudo dimension of this function class, which captures the behavior of your, as you vary the learning rate or the activation function hyperparameter, you want to give a bound on the pseudo dimension of that function class, right? And that would imply, using this classical result, a bound on the sample complexity. Okay, so recall this was our utility function, and there's classical work on neural networks which assumes that this function is piecewise polynomial. So some concrete examples where this is the case is ReLU activation. So this is one of the assumptions we need to make in order to give guarantees, but the idea is if you have, for example, ReLU activation, the neural network's behavior can be expressed as a piecewise polynomial function. So you can have boundaries which are also polynomial, and within each piece, the behavior of the network is a polynomial function. This doesn't quite apply if you use things like sigmoid activations, but that's another sort of interesting direction. And we hope that using some of the Pfaffian techniques that we introduced, we can extend the current results beyond polynomials. Right. So you have these boundary functions, H1 and H2, like, different pieces. And within each piece, there are these connected components, and the function within each piece is some kind of polynomial function, right? So there are these polynomial surfaces which capture the performance of the network for different values of the parameters and hyperparameters. And the function that we're interested in, this red function u star x, which just captures, so basically on the surface, it finds the, you think of for each hyperparameter, you're solving a gradient descent so that the gradient descent finds you the best parameter for that value of alpha or that value of hyperparameter. Just a simple 2D example so that's easier to visualize, but this is what's happening here. So you can generalize this to high dimensions, but for each hyperparameter-parameter pair, if you fix the hyperparameter and, solve gradient descent or some other optimization technique, you can find this U star function, which tells you, okay, this is the performance of the neural network for this hyperparameter, because this is the value of the best learned weights when you set this hyperparameter. So essentially, this is this U star function is the function that we want to give pseudo dimension bounds on, and this is our key result. So you can give a bound on this on the complexity of this U star function in terms of the number of connected components, the number of boundaries, and the degree of the network in each within each piece. So that's sort of the key contribution, right? A simple example of this is you have two activation functions, O1 and O2, and you have this hyperparameter which interpolates between these two activation functions at each node of the network, right? Then by plugging in these terms, you can get a concrete bound on the sample complexity of tuning this interpolation hyperparameter. And this depends on things like L and W. They are the number of layers and the number of and the width of the network and so on. So you can get this sort of concrete bound of like how much data you need to tune the activation hyperparameter. Another exciting hyperparameter, if you seen gradient descent, right? So there's this learning rate parameter. There's prior work which gives guarantees on tuning. So this is one of the earlier works which initiated this field of data-driven algorithm design. But they assume that the function that you're applying gradient descent to is convex and smooth, which for neural networks we know it's not a convex function on any typical problem that you study. So this is ongoing work where we get the same sample complexity balance, but even for non-convex, non-smooth functions. This is super exciting ongoing work that we're able to tune the learning rate hyperparameter also using some of the techniques that we talked about in this tutorial. Right. This is something you want, if you're curious, you should look out for. This should be out soon. Okay. Finally, I would like to conclude with directions for ongoing and future research. So we have a bunch of open questions. This is an exciting growing field. I showed you several slides on like different algorithms or applications, right? So it is not just limited to hyperparameter tuning and machine learning, but within the context of hyperparameter tuning, I would still say it's super underexplored at least. There are so many questions of different hyperparameters where you can give concrete analysis or provable guarantees using these techniques. We talked about techniques on statistical complexity, which is basically the amount of data you need to give guarantees that this much data is sufficient to or necessary to tune these hyperparameters. But can you give computationally efficient methods? That's, an interesting open question. There are very few works on this, and that's another exciting direction. Talking about connections with Bayesian optimization. So interesting thing about this line of work is this is complementary to Bayesian optimization. So there is hope to you put them together and get something even nicer. One ways in which it complements Bayesian optimization is that it can be used to give sample complexity guarantees even for Bayesian optimization. So what that means is, so the kind of guarantees that we give, like, are dependent on the algorithm and the hyperparameter that you're talking about. So, but they are independent of the optimization technique you use. So they just say if you get small error on the training data set, you will generalize well on future test instances which are coming from that distribution. You could use Bayesian optimization or banded-based methods to get a small training error, but whatever training error you get, your test error will be within epsilon of that training error. So it's sort of agnostic to what method you use on the training procedure. It just gives you guarantees about how much data you need. So it has nice combinations, but at the same time, there is hope that we are able to give our analysis is able to give things like how complex number of oscillations and number of pieces in these functions for these concrete hyperparameters. Can we make these approaches, Bayesian optimization-based approaches, more structure aware? Can you use this structure to somehow give even better algorithms, or at least more automated algorithms? Because now that you know how smooth or how oscillatory the function is, you can maybe set the hyperparameters in Bayesian optimization more intelligently. Well, that's some hope. We go beyond the worst case complexity. So we have, this is the question that was already asked. We have the very first work on this, which works in the case of linear regression. So we're tuning L1 and L2 penalties in linear regression. We show that you get better bounds. So, and you can actually not hope to get these bounds for the worst case distribution. So for the worst case distribution, we actually have lower bounds in the previous papers, which shows there's upper and lower bounds, which are roughly linear in the number of features. Well, that's very terrible news for high dimensional feature spaces that people typically work with. But we can get rid of that linear dependence. We can get rid of this curse of dimensionality in this particular context for nice distributions like Gaussian or even sub-Gaussian distributions. So as long as you have a nice tail behavior, you can get much smaller sample requirement for tuning hyperparameters. Right. But this is, again, the first attempt at this direction. This is a super exciting question, like, can you give more and more results for tuning, maybe more general tools or results so it does not use the pseudo dimension, it uses a different tool called raw democratic complexity, which I didn't have time to get into, but this is, again, a super exciting question. There are more challenging high dimensional settings. That's in some cases, like the activation parameter, we only solve single parameter case settings. So there's another question in several cases. Can the techniques extend to higher dimensions? The math becomes more complex. Even the computational efficiency becomes more challenging. So there are both sort of challenges, analytical as well as practical. And finally, one of the reasons why I wanted to give a talk here, specifically at AutoML, is a very exciting, applied audience, a nice connection between academia and industry. which is something I'm doing more of. So I focus mostly on theory, but then I'm working with more applied researchers. We are preparing a tutorial at Europe, so with Colin, who's at Meta, and Nina, who's my advisor at CMU. And we are, it's something I encourage other people to think about and like get back to me if you have ideas related to this. So we are trying to find more and more connections between this. So this has developed as a fairly mature theory at this point, but connections with practice is something we're still exploring, and we are very excited about. So with that, I would like to conclude, leave it open to questions. I have some references, which I'm happy to share slides. I don't know what's the procedure. I talk to the organizers if there's a way to share slides and all the materials. But if you have any questions, please ask them. Yeah.